Hey there folks, Professor Fiore here. In this video we are going to look at a current differencing amplifier. So if you're a fan of the LM3900, this is a video just for you. So the first thing I'm going to say is, if you haven't looked at the videos on differential amplifiers and current mirrors, it is imperative that you look at those first, because this video builds on those preceding bits of material. All right, let's get into it. What is a current differencing amplifier? Well, the direct comparison is with a standard differential amplifier, which is a voltage mode. In other words, we define the output voltage as a gain times a differential input voltage. In other words, voltage input number 1 minus voltage input number 2. All right, so typically if you had BJTs, we would have base voltage number 1 and base voltage number 2. You subtract them out, you get a differential voltage and multiply by the gain. Bingo, that's your output, right? That's the way a normal differential amplifier works. A current differencing amplifier is current mode. So it's similar. We have a gain times a difference in current rather than voltage. In other words, we would have a current input number 1 and a current input number 2. So we say current number 1 minus current number 2, that gives us a differential current. Multiply by the gain, we get an output. All right, great. Now, because it's current mode, typically this would be referred to as a Norton amplifier, right? You think of like Norton's theorem, all right? So current amplifier, Norton amplifier, same kind of thing. Now, how do we create the current subtraction that we need? Typically, this is done through the use of a current mirror. I'll show you a circuit in just a sec. Probably the most popular implementation of the current differencing amplifier is the LM3900. This is an integrated circuit. It's actually a quad. There's 4 amplifiers in one dual inline package. This came out from in the early 1970s, as I recall, from National Semiconductor. It's kind of a unique little circuit in that it can run on a single polarity power supply. You're going to have to add some extra things on it to make a dual power supply, you know, a normal op amp that we're used to. It has some kind of weird little quirks to it. They were very inexpensive and people liked them. But there are some quirks compared to your average amplifier, which would include the fact that the input impedance is not necessarily all that high. Right, depends on the design. The other thing is, like in the case of the 3900, the slew rate is asymmetrical. In other words, positive going slew rate and negative going slew rates are entirely different. And I mean different by like an order of magnitude. So you can't just take a normal op amp circuit you might have looked at and just throw in a 3900 and expect it to work. It won't. There are things you have to do with it. But that's not really my goal here in this video, talking about the 3900. I really just want to point out how you could create one of these things, because it's an interesting sort of idea, right? You know, you think of your typical diff amp, whether it's made with a BJT or a FET, you know, we typically have that long tail pair configuration. You know, we have the 2 sides, so to speak, that are kind of mirror images with a single master current source pulling down the tail current. You know, we've seen the videos, hopefully, or read the appropriate material in the book. We understand how that works. So this operates on a completely different sort of approach. Here is sort of a basic current differencing amplifier configuration. I've got 2 current sources back here. All right, so here's IN plus, right, what we would normally refer to as the non-inverting input, and then IN minus, right, for the inverting input. Now the main transistor of interest is over here. This is T2. And then we have this little configuration in the front end, T1, and then this transistor labeled D1. So if you remember from the current mirror, right, current mirror videos, an easy way of making a nice match on transistors, if you were to try to do this in lab, for example, is to simply short the collector-base junction of a transistor. What you're left with is the base emitter junction. So this is typically how we do this in integrated circuits. It's very easy to make a whole bunch of transistors. You make 2 transistors right next to each other, short one of the collector base junctions, and now you've got a diode that has virtually the same characteristics as the transistor. So T1 and D1 make up a very simple sort of idealized current mirror. Basically, the way this works is In minus comes in. We're going to assume all of that current goes down into D1, right? So again, just think of this as a diode. And what that will do is that current will produce a certain base emitter voltage, the quote-unquote diode voltage. That voltage is the same exact voltage that we see across the base emitter of T1. Now, if these two curves are identical, if the base emitter current voltage curves are identical, this has one voltage, this has the same voltage, we should have the identical currents. In other words, the current coming down through here, this diode current, literally I of D1, would have to be mirrored, would be identical in T1 over here. So what we're really doing is taking this current and sort of mirroring, literally, that current and subtracting it. Notice the direction, right? The current coming in, it's going down like this. We're going to pull current down. So that current literally gets subtracted from In plus. So I've got 100 mics coming in over here, 20 mics coming in being mirrored. So I'm going to subtract the 20 mics. And what we should have is the input base current for T2 would be the difference, or 80 microamps. Now we are making some approximations and simplifications here. For example, we're ignoring the effective base current into T1. All of this 20 mics does not go down through the diode. Some of it goes in here. So this is not going to be perfect, first thing. All right, we'll see just how close it is in a sec. A couple of little caveats. I put a note over here. The way this is configured, In plus has to be bigger than In minus. If these were swapped, in other words, if this was 20 mics and this was 100, subtracting that would give you a negative current. That's not going to work because now you'd be pulling current out of the base of T2. Forget about it. Not going to happen, right? These current directions have to be in the direction shown, right? In plus and In minus have to be going in to the two inputs. You can't have negatives out here, right? So, in the case of the 3900, I mentioned earlier that these things are normally set up for a single polarity power supply. That's why, okay? Now, let's do a quick sim. Do a little DC analysis over here. See what we get. All right, so I said we were supposed to get 80 mics over here, and we're actually getting 81 and a little bit of change. Ugh. So like I said, this current, right, this base current, we ignored it. Well, okay, that's part of the error. I mean, that's could be 1% of the error right there. The other thing is this collector base junction here is shorted. It's 0 volts. That's not the case for T1. So if I come over here and look at the voltage, right, I can see this is just about 0.8 volts. And on this pin, we're getting a little over half a volt. So that difference, right, is not 0 volts. And that will create a little bit of an imbalance here as far as the mirroring is concerned. All right. So how are we going to fix this? Well, let's use a better current mirror. So in the current mirror video, we looked at a bunch of variations on the theme. This is one of them. I am not going to go through this whole thing, but I'll just call out that D1 and D2 are in fact diodes. That other video on the current mirrors explains exactly how this works, but for our purposes, we can just say this is a more exacting current mirror. All right. What do we get out of this? Okay, so here's the 100, here's the 20. Ideally, we'll get 80 microamps over here. And we'll do a little check. And sure enough, we get 80.0477. So, we're under 1/10 of a percent as far as the inaccuracy. All right. So we can see the way this is working, right? This comes in, creates virtually 20 mics down through here, gets subtracted off, goes into the base of T3. That gets multiplied up by the beta. We get an output current. Now, I'm not showing a resistor out here. You might use this current as is, the IC in transistor number 3, or you might have a resistor in here and tap off a voltage. So you'd have a voltage that would be a scaled version or associated with the difference in the input currents. All right, so this is not necessarily the case. You would have to have a current mode output. You could create a voltage mode output. But basically, that's what's going on here, right? So like I said, if you have used 3900 or you have a circuit or something you want to experiment with, Just be aware this is a different sort of operation mode than your typical op amp. It's current mode rather than voltage mode. And like I said, this is basically one way of doing it. This is probably the most common way. This is the way to think of it as an equivalent circuit. Simple diode transistor creating a current mode, creating a current mirror that draws the current out of the other input, and you have a differential input current. But again, don't forget these little limitations, right? IN plus must be greater than IN minus, and the currents have to be in the direction shown. Okay? Beauty! Hope you enjoyed it. We'll see you next time.